We know that, given two functions f and g, the derivative of their sum is the sum of their respective derivatives. Now consider the function f times g. We might think that the derivative of the product is the product of the derivatives, but it is not so. To convince ourselves, let's consider an example. We take both f and g equal to x, so f times g is the function x squared. The derivative of f times g is 2x, while the derivative of f and g is equal to 1, and therefore their product is equal to 1. Clearly, 2x and 1 are two different functions, so it is not true that the derivative of the product is the product of the derivatives. The link between the derivative of the product, f times g, and the derivatives f prime and g prime of the two factors is more complicated. It is in fact given by this theorem. If f and g are differentiable at x, then the product function f times g is also differentiable at x, and its derivative is given by f prime times g plus f times g prime, where each function is evaluated at x. Such a formula is known as the Leibniz rule. Let's see an example.
Let's consider the function f of x equal to square root of x times exponential of x, which is a product of two functions, square root and exponential itself. Let's compute the derivative f prime. The Leibniz rule says that the derivative of the product is composed of two pieces. The first one is the derivative of the first function times the second one, namely the derivative of the square root of x times exponential of x, the second one, plus the first one times the derivative of the second one. Now let's compute the derivative of the two elementary functions, square root of x and exponential of x. Firstly, we notice that square root of x can be written as x to the power of 1/2. In other words, we can write square root of x as the power of x to r, where r is equal to 1/2. The table recalls that derivative of the power x to the power of r is equal to r times x to the power of r minus 1. In our case, means that the derivative of x to the power of 1/2 is equal to 1/2 times x to the power of 1/2 minus 1, which is 1/2 x to the power of minus 1/2. Let's consider the derivative of exponential of x. Look at the table, the derivative is exponential of x. Now, we can put all the pieces together, concluding that the f prime is equal to 1 over 2 square root of x times exponential of x plus square root of x times exponential of x.
From where the Leibniz rule comes from? We can get a very intuitive geometric idea of its validity, which will also help us to remember the way in which f and g mix together with f prime and g prime to determine the derivative of the product. Suppose that the two functions f and g are both positive and increasing. Let's fix x and consider a rectangle with sides f of x and g of x. Then the product of the two numbers f of x and g of x represent the area of this rectangle. Now we increase x by a small positive quantity delta x equal to h and represent f of x plus h and g of x plus h, elongating the sides by the quantities delta f and delta g, respectively. The area of the big rectangle obtained in this way is, of course, the product f of x plus h times g of x plus h. We are now ready to study the derivative of the product function of f and g, which we denote by big F. The derivative of big F at x is the limit as delta x approaches 0 of the difference quotient of big F at x when the limit exists. In our construction, delta x equals h, delta big F equals big F of x plus h minus big F of x, where big F of x plus h is the area of the new rectangle, while big F of x is the area of the starting rectangle. So delta of big F equals the sum of the areas of the three colored rectangles. The first rectangle has area delta f times g of x. The second one has area f of x times delta g. And finally, the area of the third one is delta f times delta g. Therefore, the difference quotient of big F is the following expression, which can be written in terms of the difference quotients of f and g. The derivative big F prime of x is obtained by passing to the limit for delta x approaches 0. The difference quotients of f and g tend to their respective derivatives, while delta g tends to 0, bringing the last term to 0. As a result, we obtain the derivative of big F. Recalling that big F is f times g, we get the Leibniz rule.